Hi, this is an AP chemistry video. This is topic 3.6, deviations from ideal gas law behavior. So ideal gases, in kinetic molecular theory, we know that the collisions between the gas particles are perfectly elastic. There's no attraction or repulsion between the particles. And the particle volume is negligible, so we consider it essentially zero. So if all of that's true, then we can use our ideal gas law, PV equals nRT. Real gases uh, occur. By the way, most gases do behave ideally, especially for what in high school or in college, even what you're going to deal with. But gases can be condensed, and then those particles will be attracted to one another and repelled. And this can happen at extremely low temperatures or high pressure. So anytime you're getting those gas particles closer together, and then the molecules do vary in size. They do have volume. So if a real gas PV is not going to equal nRT. There's definitely equations to calculate corrections. We're not going to do that. We're just going to look at it more conceptually. So if we are at STP, which is 273 Kelvin, which is 0 Celsius, which is still relatively warm, 1 mole of a gas at STP, which pressure is 1 atm, 1 mole will occupy a volume of 22.4 liters. So this is assuming all of the kinetic molecular theory assumptions. So therefore, we would say the particles have no attraction to one another. But a real gas, if there are significant attractions between the particles, then the collisions between the particles in the container are going to be less. And then the actual pressure is going to be lower than what it would have been. So if these particles that collided are now attracted to one another, there's going to be less colliding with the sides of the container, more attraction to each other, less colliding with the container, so the pressure is going to go down. Anytime you have really increased intermolecular forces of attraction, that pressure that we see for the real gas is going to be smaller than what we would predict for an ideal gas. Unless we have really high temperatures. So high temperatures, those IMFs become negligible. Particles are moving so quickly that they can't really interact with one another. But at low temperatures, the IMFs are going to become significant. They're going to be attracted to one another, not be hitting and colliding with the container, and the pressure is going to be lower, and we're going to get non-ideal or real gas behavior. Molecular volume, so the size of the gas particle, if it's behaving ideally, we assume the volume is essentially negligible and that it really doesn't matter. But for a real gas, if as the particle volume increases, there's less freedom to move and collide with one another. And therefore, actually, just wait, the number of collisions with the walls is going to increase. So the pressure is going to be greater than 1 atm. So less space, there's going to be more collisions with the container, and that's going to lead to a higher pressure than what an ideal gas would have. So if the volume of the particle is big enough, then the space in which they move is small. Therefore, the collision frequency with the walls of the container is going to go up, which is going to cause the pressure to be greater. Also decreasing the volume of the container. So if we use the ideal gas law, if we decrease the volume by 1/2, then our pressure is going to double. So those are inversely related. a real gas, as the volume becomes smaller, the particle volume becomes more significant, like we were just talking about, and the pressure is going to be greater. So if I reduce the volume enough, so if I originally have this, and now they only have this much room, now that volume of the particle is going to get more significant, less space in between, more collisions with the container, causing a greater pressure than would be expected. So if the volume is halved, the pressure is much more than 2. It's going to be greater than 2 or doubled. Yeah, which I have over here. The effect of the particle volume. So as the particle volume becomes significant, as they get bigger, the pressure is greater than we would predict, which we were just talking about. At low pressure, the space between the molecules is really big. So then the molecule volume doesn't matter as much, and the gas is going to behave more like an ideal gas. At a high pressure, the particles are going to be in closer together and have less volume to move in, and therefore they're going to create a greater pressure and not behave ideally. They're going to behave as a real gas would. So you can see this diagram here is showing high pressure. The volume of the particles is way, you can see there's a lot less space here for movement, and the particles are going to have a chance to hit the sides of the container and exert more pressure. So in summary, when do gases exhibit non-ideal behavior? It's when you have a low temperature or a high pressure. Both of those are going to cause the particles to be closer to one another. And there's going to then be significant attractions or repulsions. So there can be intermolecular forces of attraction. And the particles, the volume of the particle will then become more significant. So here is kind of a summary of what we were just saying. So let's try this example 18. I would try this, pause the video, and then see if you agree. So in this question, which of the following gases will behave least ideally at a pressure of 1 atm and 300 Kelvin? The one that's going to behave least ideally is the one that's going to have the greatest IMS, because then there's going to be some attraction between the particles. If there's an attraction, the higher the IMS, the lower the pressure, because the particles aren't as likely to collide with the container because they're attracted to one another. So I would look at all 3 of these have only London dispersion forces because they're all nonpolar. The strength of the London dispersion is stronger for the chlorine, but that is not our choice. We would want to pick letter D because the HF has, it's a very polar molecule with hydrogen bonding. And that is a significant type of intermolecular force that's strong, and that will result in non-ideal gas behavior, such as the pressure being less than what we would expect. Let's try this one. Under which temperature and pressure conditions will a gas behave most ideally? So if you remember, they behave at most as real gases if you have a high pressure and low temp. They behave more ideally at low pressure and high temp. So we look at our options. We want to pick a high temperature. So we're going to pick between A and B. We wouldn't pick these because they don't have as high of a temperature, and then we would want to pick the low pressure, which would be B. And that is all I have. I hope that helped you to understand some of the deviations in ideal gases behaving as non-ideal gases.